A warm greetings to one and all. I'm Sai Parmeshwari from CSCAML B section. Today we are going to discuss a topic about transitional circuits. Here I give the content that we are going to discuss in this topic. Early history, impedance of uh, impedance transition by partial cumulation, impedance transition by full cumulation, trans, uh, translation on transfer functions, second order effects, reference. Earlier history. The use of time variant systems for the transfer of transfer functions date back to the late 1940s and early 1950s in their 1948 papers. Business all Dishal proposes the argument shown in Figure 1, where a mechanical wheel holding a number of capacitors rotates at the rate of F turns per second, allowing each capacitor to uh, charge to the input and half cycle later discharges at the output. The input output transfer functions disappears as in figure 1b, revealing a com, com filter response with a band pass peaks located at the harmonics of F. Transitional circuits are providedly driven time variant systems and encompass topologies such as cumulated networks and n-path filters. These systems cause frequently translation of impedance and transfer functions, a useful property that has led to myriad new and interesting concepts in RF design. We study the operation principles of these circuits. This is the figures of 1A and 1B that we discussed past. Impedance translation by partial cumulation. Transitional circuits can shift an impedance to a well-defined counter frequency. For example, the impedance of capacitor can be translated to a center frequency of LO, taking on the form 1 by C LO at it is equal to LO rather than at equals to 0. It is section we investigated how the translation occurs due to switching activities. Cumulated networks can proceed a non-cycled voltage in response to a synodal circuit. To find the impedance, therefore, we must compute the first harmonic of the voltage. This is the figures of 2, 3, and 4. The analysis circumstances of the following observations: a synodal circuit of frequency F in equals to R in by 2 LO can proceed a very large voltage swinging at fin between nodes A and B in figure 5b, revealing that the equivalent impedance of the switched capacitor is very high at the frequency. This situation stands in constant that in figure 5a, where C1 is a low impedance at fin. We therefore conclude that the impedance of the capacitor is translated to a center frequency of FLO, emerging as 1 by C LO. Of course, this property arises from the bilateral nature of the switch. The voltage across the capacitor is mixed with the LO and upconnected as it manifests itself in VAB. We call this circuit's operation partially commutation. The emphasis that Lin does not see a capacitance for half of the LO period. What happens if fin in figure 5b 5b this is 5b departs from FLO, the synapticity between Lin and the LO no longer holds C1 receives both positive and negative charge from the Lin, and the capacitor voltage grows to a lesser extent large enough. We can say that when S1 is on the swing in VAB is approximately proportional to 1 by C1, and when S1 is off, the switching is proportional to R1, a much greater value because RC1 1 and 10. We can thus approximate C1 by a short circuit and reduce the current that in figure 5D. Here VTAB, so we must seek the component of VA bat this frequency. Since ST has a DC value of zero point 0.5, the amplitude of VAB at fin is given by zero point 0.5 IRO. Impedance translation by full cumulation. We should make two remarks. First, the conditional RC1L and TO is necessary for significant up conversion of the capacitive impedance each time has a switch turns on the corresponding capacitor. Impressive voltage upon the output. The longer this voltage lasts, the more pronounced is the effect of capacitor plotted in figure 7 is the output voltage for the extreme cases RC1L and TO and RC1L percentage to TO reveals a specifically reach signal in the former that steams for substantial upconversion of a capacitor voltages in the lateral. On the other hand, each capacitor rapidly loses its charge when it is shifted in, allowing VAB to assume the shape of Lin. The key point there is that the cumulated network need not be driven by a high source resistance too large as RC1L and TO. Second, the translation of the capacitive impedance in figure 6a also occurs at the high harmonics of the LO. For example, an input of the form I in 0 sine 3 LO leads to accumulate of charge on C1 and C2 and a tall wave force of VAB. Translation of transfer functions. Applying this product producer to a first order RC filter yields the circuit in figure 8a and a band pass response around FLO. Similarly, as deflected in a high pass section can be converted to a noted filter center at FLO. In both cases, RCS must be greater than TLO. Smith expression 1 by NRRSC is included in that it implies a reduction in a bandwidth as the number of cumulated capacitors increases when through only one capacitor is tried to the output at a given point in time. This puzzle can be solved if a recognizes in figure 8a that the dwell time of the capacitor, the pulse width of the LO phase decreases as M increases. Constantly, each capacitor has less time to interact with the length and our stand experience a smaller voltage changes as it value were larger. Bond order effects. A number of phenomenon graded the performance of cumulated networks and require attention. This include the on uh, resistant of the switch RSW, the translations of the source impedance, and the finite rise and fall times of the LO. The other 5BD reduction in the peak implementation impedance in figure 6b arises from the overlap between the LO phases, creating a temporary receive path between the top terminals of C1 and C2. The overlap may simplify occur because LO and LO has finite range and fall times, keeping the two switches on simultaneously twice per period. Reference H. Bergens and H. Dickens some relation between speed of indications bandwidth and signal to random notice radio. In radio navigation and direction finding processor IRE PP 478483 May 1948. Analysis B.D. Smith Analyzing of Commutated Networks IRE Transfer Professor Group Aeronaut PP 21 to 26 December 1953. Thank you.